So I guess time is almost up for the this afternoon session. So maybe you can begin. Okay. So the first speaker this afternoon is Hiroshi Itoyama, and the title you can see here.
Thank you very much. First of all, I express my thanks to the organizer and the local organizer this symposium, and I'm very pleased to be invited to this series of this year of East Asia Joint Workshop on Field 3. And this year, I'll be discussing the work-time collaboration with a graduate student of our group, Sota Nakajima, where I had an occasion, I had an opportunity to bring to be back to my old work, which was done in about 30 years ago in collaboration with Thomas Taylor, and the two of us were at the program at that time. And I will be able to discuss basically the two-parameter extension of the work done with Thomas Taylor in the next half an hour. In the modern motivation and in the best notation which I have at this point. Okay, so I would like to call your attention to the SO16 processes 16 non-supersymmetric heterotics in intended dimension, because that I think is receiving revived attention. Why is that so? Because there appears to be no supersymmetry in the multi-B scale, so according to the C experiment. So supersymmetric breaking scale, it should be much higher, if not at the Planck scale. So therefore there is an obvious interest to this modular invariant, the only modular invariant algebraic non-supersymmetric heterotics in 10 dimensions. And moreover, this, and this was done by Erickson, Harvey, and Albert Gomez in 1986. And here is the logo of the new institute, which was founded last November. It is called the Nambu-Yoichiro Institute of Theoretical and Experimental Physics in our university. The member of the institute is also at the same time member of the physics department. In addition, there are several people which are hired last year. And it covers all regions of the theoretical. Basically, it covers almost all regions, branches of theoretical and experimental physics. And not only do we promote ourselves by working harder, but also do we like to serve to the community by hosting several important symposiums, such as this one. And I like to I ask for your cooperation in this regard. This is the rule. Okay, so how do we discuss that? Basically, I'm going to interpolate two heterotic vacuum, the one supersymmetric one, the other the non-supersymmetric this one. And in doing so, I'm going to compactify the model by doing a twisted circle compactification. And there is a formula which I knew for some time, because cosmological constant of this model is an important observable albeit being in 9 dimensions. And I knew for a while that the formula basically takes a following form in the supersymmetry restoring region. Restoring region means in the region where I increase the radius or decrease the radius depending on the rotation. Today I increase the radius to order infinity, so supersymmetry is restoring, but not quite exactly. In this asymptotic region, I knew for a while that the formula for the vacuum energy density takes this one. And since I received several questions in the last few months by by the workers, I decided to include some explanation, more detailed explanation in the next slide. So please keep in mind. Okay, so in this work, as I said, we consider two-parameter extension of this interpolation problem by putting an Wilson line, a single Wilson line. So we examine the interrelationship among the twisted compactification, gauge symmetry, enhancement, and the cosmological contact. This is so this explains the title which I put at the beginning. Technology I introduced is more or less a bread and butter technology, which were more or less established at the beginning 5 years of the superstring revolution. But probably many of them belonging to the younger generation were not born as a scientist, so I explain some technology and the interpreting model with no Wilson line, which were done with Thomas and myself some time ago. And then now I will discuss the work with SOTA with one Wilson line. So far we were able to put just one Wilson line, and we are working for the extension of this problem. For the sake of presentation, I will discuss the SO32 case only today. But although we completed two models, two interpolating models, SO32 versus non-supersymmetric, and E8 versus non-supersymmetric one as well. I'll just mention this case at the end for the results. Now, as I promised, I would like to explain the formula for the cosmological constant. The first term is an algebraic decaying part, which is whose coefficient whose coefficient constant times the number of massless fermions minus number of massless bosons. Maybe you are more intrigued with the second term, namely y. The massive contributions are exponentially suppressed. Let me explain that point. This is in the supersymmetry restoring region. So it's almost there are almost the boson fermion cancellations are almost working, but not quite so. This can be understood as an lattice SO1 momentum lattice with for the integer momenta minus that of the half integral momenta. So there is some approximate supersymmetry realized in Carter-Klein excitation. And so this is boson and this is fermion. So this forms an asymptotic approximate supermultiple. And this acts as an Suzy restoring factors. And I kind of assume your knowledge of the vacuum one loop amplitude for the string theory, which is essentially sum over all boson and fermion particles with loop in the form of proper time propagating. And of course, there is a question of modular invariance and cutting off the short distance part, but this doesn't play an important role here in this discussion. So generic massive level contribution can be written like this, and here the mass splitting of the broken supermultiple is like alpha prime 1 over ms squared to be 1 over a tilde squared. And a tilde is going to infinity. The point is that you apply the Jacobi imaginary transformation for this object to convert tau2 dependence in the exponent over the 1 over tau2 dependence. Then this can be easily bounded by taking the geometric mean. So the generic massive contribution after summation is easily bounded by this expression. And if you send a to infinity, you see that this is exponentially suppressed, and we can integrate over the large time region for m not equal to 0. For m equal to 0, namely massless level, you perform term by term integration over this large time region, and you are able to disarm this expression for this case, and you get something like a transcendental number of zeta n or so. So this is how the first term occurs. And this, the first term is algebraically decaying up to an exponential accuracy. And as for the term, for the short time region, it's completely safe thanks to the string theory. So with simple inspection, you can check that this is exponential accuracy as well. So this is how this formula works basically. In the region, supersymmetry is restoring, but not quite so. So, as the title indicates, we would like to hunt for a possibility where the gauge symmetry enhancement occurs and simultaneously exponentially, cosmological constant is exponentially suppressed. And we have found one example, namely a series point in the parameter space where this is occurring. But now we think that exhausting all the possibilities can be more important, just limiting ourselves to that possibility. Let me go on. So maybe it's not necessary to go over the idea of heterotic string, but I have my slide in any case, so let me quickly go through that. Everyone knows heterosis, left mover, right mover the superstring, and the left mover the 26-dimensional bosonic string with 16-dimensional internal coordinate where you realize rank 16 current algebras. And for today's talk, only state counting is necessary. So state counting, in state counting, which is essentially the integrand of the vacuum amplitude, is this one. And these are the left and right Hiroshi generators. And you expand in terms of Q. And if you do that, the integrand takes a form of like this. But instead of working with the Virasoro character, it's better to work on SO to N characters in various dimensions, because SO to N character involves space-time and internal symmetry groups. So there are 4 characters, O, vacuum, V, delta, and 2 of the spinor characters, which are expressible in terms of 4 theta constant and the data function. For example, SO32 heterotic string takes this form. Of course, this is 0 after Jacobi abstract absolute identities, but it's better to write this way in order to represent the particle content of the theory. This is the example. So SVOC, please remember, and not to be confused in grammar of the English. Okay, so now how do we construct the interpolating models? We start out from a well-known expression, say 10-dimensional string model N1. Suppose this partition function takes the following form, namely 8-dimensional bosonic part plus some internal part, typically, which includes typically the contribution from the fermionic strings. And in the most well-known example of circular compactification, where you identify nice direction of the coordinate with the one shifted by 2 pi r, the left and right moving momenta along the compact 5 dimension takes values on the SO1,1 Lorentzian lattice, which are labeled by 2 integers, n and w, which are the momenta and winding numbers, and the partition function after the compactification takes this form, this well-known form. But in this circular compactification, you just get back to the original model in the other limit. You have to twist circle in order to reach the other model. And so let me explain how we do that. It's called Z2 twist mode. Z2 twist. You need to introduce Z2 twist. Z2 twist is not just Z2 operation, not just Z2 operation in the internal coordinate. It includes the half translation in the compactified circle. And for today's talk, I work on the T-dualized coordinate for the compactified dimension as opposed to the original coordinate. You don't have to do that, but we somehow began with this notation, so let me go on with this. There, you start the original model relied on the R equals 0, and the other asymptotically Suji region is realized as R dual goes to infinity. Okay. So because Z2 twist contains this half translation, partition function of the interpolating model contains a set of four momenta lattice which we label this way, and alpha beta 0 and 1/2, x 0 and 1/2, and imply integer or half integer momenta, or even or odd or winding numbers.
So is it different from RT1?
Huh?
RT1, not S1, but is it?
It's not. I don't think it's not. It includes space-time translation together with Z2 operation.
What is it?
Z2 is out of the internal part. So let me. Goal is to construct a modular invariant partition function from this Z2 twist action, which is TQ. You start out from the ordinary, the expression we started with, which I showed you in the last slide, but in the end, instead of all winding number, I just write it as an even winding number plus odd winding number. And the part which is odd winding number changes sign under the half translation, therefore we get a minus sign. And then, but this is not going to be modular invariant, so we need the recipe is that you make a S-dual action where tau goes to minus 1 over tau, and then followed by that, you act TQ action. You act on the TQ again. And the resulting action is defined to be an model, our interpreting model, and one can show that this recipe provides you a modular invariant partition function. And in the other limit where A goes to 0, this interpreting model produces another model, M2, whose partition function is this one. And M2 is, of course, directly obtained by Q twisting model in 1, because in the other limit, this half translation is void. So let me repeat essentially the idea. You start out from the model A or model B, and by this twisted, you make a twisted compactification, and model B is obtained like this. For instance, in the model we took, model A or model 1 will be SO32, and the model B will be is SO16 plus SO16. And following the recipe which I just gave you, so we immediately got the partition function of the integrating model. And I already explained these things. And in one limit, you get a contribution from 0 winding number only, and you get back to the only the momentum lattice survives, and in the other limit, only the 0 beta part survives. So this is kind of repetition. In the R infinity limit, in the limit, this interpolating model, one loop function of this interpolating model becomes heterotic, the one with the heterotic string, and the supersymmetry is restored. In the other limit, where this is true, then you get one loop function for 16 processes. So 16 heterotic strings. And at the generic radius, one can check the mass spectrum, which is a kind of simple exercise. And then you can check that it comes from the zero momentum and the zero winding number part, which is in the first line of this expression. And the mass states at the generic are well-known gauge boson and graviton multiplex. And the number of massless fermion minus number of massless boson is 64. Okay, now here is our starting point of our calculation. So far, we have introduced only one radius parameter, and then we are going to put the Wilson line on top of it. So it's a two-parameter model as opposed to one parameter model.
So let me make sure. So you compact by two directions?
No, one direction and put Wilson line.
What do you mean by this compact radius? I don't understand this horizontal. That means I don't understand.
Radius you can choose.
So how do you break the triviality? I mean the R to, I mean the alpha prime over R. So this breaks that triviality, right?
Yeah.
How did you do that?
No, this is a kind of twisted triviality.
But one is Suji broken, right? And
One is Suji broken, and the other is the superstring.
But do they dual each other? Are they dual each other?
Yeah, I'm able to. I told you that we are able to interpret too. This is what we mean by twisted computation.
Yeah, please.
So we are going to put another parameter, namely we put Wilson line on top of it. And the Wilson line on the action takes this form with the parameter capital A, and omitting some detail that putting on the action, putting on the Wilson, putting on this term to the worksheet action amounts to boosting and followed by rotation of these three parameters of the internal moment, left momenta, and left and right momenta in the 9 direction. Boosting. Yeah, the boost followed by the rotation takes this form after skipping some explanation. So this is essentially the map from unprimed parameter to a set of primed parameters, and with this transformation, a combination of lattice with some theta characteristics raised to the 8th power is transformed to this expression, where gamma delta can be summed. So the expression gets convoluted a little bit. Then the argument is written. Argument of the lattice is written in terms of the transformed variable. So it is again immediate to write down this interpolating model in the presence of Wilson line. You just change notation a little bit and its meaning. Namely, you write 016 instead of 016 in the last slide. You write 00, and this boosted lattice expression. And this is basically the expression for the new model in the presence of the single Wilson line. And let me check that the two extreme limit r equal infinity and r equal 0 for an arbitrary value of Wilson line, just for check. And then in the limit of r infinity, then you get back to this expression. So we recover the SO32 supersymmetric heterotic string one-partition function, which should be vanishing because of V bar equals S bar. The other limit, this part gets died away, and then we get one partition function of SO16 plus SO16. So, as is expected, we are able to interpolate these two supersymmetric and non-supersymmetric heterotic models in the two extremes for an arbitrary value of Wilson line. What about in a generic R and A? Then the massless spectrum comes from, again, the first line of untwisted sectors. And as one expects, that we get massless boson include graviton multiplet, and gauge group gets broken by the presence of Wilson line. So SO16 cross SO16 is broken down to SO14 cross 0 and gravity. And then the massless fermion takes this form, and the number of massless fermion minus the number of massless boson is 32. So here is what we expected. But there are a few conditions under which we get the extra massless particles, and we can look for it carefully. And there is a point, there is a condition in which extra massless particle appears by looking at this point. Here is the first condition, written in terms of A and capital A and lowercase a. And then for this case, we see that gauge enhancement occurs, which gets back to SO16 to SO16, and the number of fermion minus number of massless boson is equal to 64. And another possibility is we found that this pattern, there is a possibility that extra massless particles appear from the third line of the line here. And the condition turned out to be expressible by this. And then the gauge group gets enhanced into SO18 cross SO14, and in this case we found the number of massless fermion is equal to the number of massless boson, accomplishing exponential suppression in the SUSY restoring region. So this is basically the report of our computation, or rather simple computation afterwards. So let me summarize. We have added Wilson line background to the radius and constructed two parameter interpolating models, and have found we completed the calculation for SO33 case and the EH cross EH case, and have found the condition for two parameters under which gauge group enhances. And we found one example under which cosmological constant is exponential suppressing simultaneously with gauge group enhancement in the SUSY restoring region. And here are tables. And here, eventually in the paper, we wrote two parameters as tau1 tilde and tau2 tilde, parameter space of tau1 tilde and tau2 tilde. And so there are three orbits, and where the tau to infinity point is a kind of supersymmetry restoring region. And here is also, this is a table for the EH plus EH case, where we find not only positive algebraic decay, but also negative algebraic decay. So this is exponential vanishing, this is dosita, and dosita. So common folklore said that the point of the gauge, point where gauge group gets enhanced are going to be the extreme of the d-dimensional vacuum energy density. So it is up to you what happens to guess what happens when we put two or more. Oh my God. Okay, so. So talk is almost ended. So it's up to you what happens when two or more lines are added, and
this is the end of the cosmos and line.
Process.
I'm sorry. Maybe this tell that I shouldn't tell you the conclusion. Okay, so what happens? It's up to you to guess what happens when two or more Wilson lines are put. Our preliminary indication that there will be some unstable direction for this in this naive perturbation theory, and the other issues are what happened to this kind of compactification were accomplished until down to 4 dimensions, and there are of course issues of higher loops where string calculation are kind of inadequate. Thank you.
Okay, any questions or comments?
Can you construct similar model for type 1?
Deep brain models, according to us, are kind of complicated. So I'm happy with hetero.
Okay. Maybe you mentioned that a little bit, but if you estimate the mass for the modularity, do you expect it to be unique or massive?
The generic massive contributions are exponentially suppressed, and
maybe my question is whether this radius direction is stable.
the currently we are putting the second Wilson line, and there is some instability introduced by the second Wilson.
So will the radius going to be larger or will it shrinking? Do you know whether it's which way?
We don't know yet.
Okay, just one more question, if any. And I do not see any more. And so let's thank Hiroshi again.